All right, we are going over the Unit 1.4 review sheet. So let's get started. First question says you've got to write an isotope symbol for these elements. Well, if it's got 16 protons, that's sulfur, and we know we always put the atomic number in the lower left, and then we put the mass number in the upper left. So that would be 32 because you add the protons plus the neutrons. Same thing for nickel. It says nickel's got a mass of 60, and then you actually have to look up nickel on the periodic table to figure out what number it is, and it happens to be number 28. So a 28 goes in the lower left. All right, number 2. Predict whether the following combinations of protons and neutrons would be stable. If it's stable, write the symbol of the isotope. If unstable, write unstable. Hint, you may need to use your band of stability graph. Actually, you do need to use your band of stability graph. So 15 protons, 25 neutrons for the first one. So let's go to our graph and let's figure it out. 15 protons would be approximately, get my pen here, right here. And then up to 25 neutrons, 25, looks like it would be right on the edge. So for that first one, it would definitely be unstable because it's on the edge. Unstable. Now let's check out the second one. 28 protons, 32 neutrons. So go back to your band of stability. Figure out approximately where the 28 would be. It would be just before this line. And then up to 32, looks like it would be smack dab right in the middle of the band of stability. So it says if it's stable, you are supposed to write out the symbol for the isotope. So you have to look up number 28, which we just did. That's nickel. 28 goes in the lower left. And then 28 plus 32, that makes 60. So it's actually the same one that we were talking about in number 1 here. Letter C. What are 2 ways you can use to identify if something is radioactive? Well, first way, if it has greater than 83 protons, it's going to be radioactive. That was something from the notes. Another way you can tell is you can actually map it using the band of stability, and if it's on the edge of the band, then it's also radioactive. Edge equals radioactive. Number 3. What's the range of neutrons possible for an atom with an atomic number of 50? Write the symbols for any 2 stable isotopes for this element. So there's going to be lots of answers, but let's go look at where 50 would fall on here. So I'm going to go right to the 50 and go up. So it looks like anywhere between 60-ish and, I don't know, 72 could be stable. I think in my answer key I actually end up saying 58 through 75, but you know, somewhere in that range, about 60 to 72. So what are some potential stable isotopes that this could have? Well, if it's number 50, it's definitely tin. So you write the symbol for tin with a 50. And then let's choose 60 for one of the numbers of neutrons. 50 plus 60 is 110. And another stable isotope could be 50 plus, maybe you choose 70, closer to the higher end. That would be 120 for the mass number. Lots more answers too. You could choose SN 50 and right in the middle. That would probably be the most stable of all of these answers. That could be an option as well. Okay, number 4. Now it's talking about neutrons. If something's got 40 neutrons, how many protons could it have? So you go back to your graph and you say, okay, 40 neutrons, go over to your band, anywhere from like 30 to 40, anywhere in here. Okay, I think on my original answer key I did it a little more exact, like 29 to 40 or something, but you know, you get the idea. These answers aren't going to be exactly the same. About 30 to 40 protons. So what are some possible elements that this could be? Well, you just list out some possibilities, like element number 30 is zinc. Okay, and if you've got your periodic table out, you can choose anything 30 to 40. So I could also choose gallium. Number 35 is bromine. Okay, lots of possibilities there. Anything with the atomic number between 30 and 40. Number 5. What happens to the neutron to proton ratio as atoms get larger? Use two different elements as examples to support this. So, as your atomic number increases, the neutron to proton ratio increases. Here's an example. For calcium, a typical calcium atom has 20 neutrons, 20 protons. So you can see that's a 1-to-1 ratio. Something like uranium has 146 neutrons to 92 protons. So you can see that's a different ratio. That's not 1-to-1. That's like 1.5 to 1. Number 6, describe two forces that exist in the nucleus. Well, there is the electrostatic force. This is the repelling force. The protons are positive, and so they repel each other. And you'd think the nucleus would want to fall apart, but there's a different force in there, the strong nuclear force. This is the attractive force that holds protons and neutrons together. It's like the glue. I'm going to say attractive, it's like the glue. Alright, number 7, we've got to fill in the blanks for these. This is tricky because this is asking you to predict the original atom before it underwent beta decay. Well, we know in beta decay the atomic number goes up by 1 and the mass stays the same. So let's start with the mass because that's the easy part. And if this went up by 1, that means it started as 75. And then use your periodic table. Re is the element that's number 75. Letter B is a little different. This gives you the starting material and it says it's losing a chunk of itself. It's undergoing alpha decay. So we need to subtract. 256 minus 4 is 252. 103 minus 2 is 101. And that happens to be MD. And this is an alpha decay, just to be a little more thorough and label these. And back over here, this was a beta decay. Number 8, write equations for the following types of nuclear decay. Sodium 24 undergoes beta decay. Well, we know that that means that that is the mass, so that goes in the upper left. If you look up sodium, it's number 11. If it undergoes beta decay, it's going to lose this beta particle. The mass number stays the same. The atomic number goes up by 1. You can also say to yourself, 11 minus a minus 1, that's 12. That's a new element. That's Mg, magnesium. How about platinum 175 undergoing alpha decay? If you look up platinum's number, it's 78. If this loses a chunk of itself that has a mass of 4, 2 protons, 2 neutrons, you need to do a subtraction. 175 minus 4 is 171. 78 minus 2 is 76. That's a new element, OS, osmium. Number 9, show any equation where the fusion of two atoms makes a carbon atom. There are so many possible answers here. So let's just make it easy. Let's start by saying, okay, this is what we're trying to end up with, and two atoms are going to add together to make that. Let's just keep it easy and make one of them a helium atom. So 4 plus what is 12? That would be 8. 2 plus what is 6? That would be 4. So this must be a Be, beryllium. Explain what it means for an atom to be radioactive. That means that it is spontaneously decaying. It emits particles, energy, or both. That is the definition for radioactive. Number 11, describe what happens to the nucleus during each of these things. During alpha decay, 2 protons and 2 neutrons are lost. Total mass change of 4. During beta decay, a neutron becomes a proton. During nuclear fission, a nucleus is split, and during nuclear fusion, 2 or more light nuclei, meaning small, combine to form a larger nucleus. If you've got 20 grams of a radioactive sample and its half-life is 250 years, how much is left after 750 years? Okay, so after the first 250 years, there's only 10 grams left. Another 250 years, there's only 5 grams left. That's a total so far of 500 years. It asked us to go 750 years, so another 250 years gets us to our final answer, 2.5 grams. Number 13, assume the half-life for something is 50 years. If you start with 400 grams, how long will it take so that only 6.25 grams of the original sample remains? Well, after the first 50 years, there's only 200 grams left. After another 50 years, there's only 100 grams. After another 50 years, there's only 50 grams. After another 50 years, there's only 25 grams. After another 50 years, there's only 12.5 grams. And after another 50 years, there's only 6.25 grams. So then we add up all of those 50s, 1, 2, 3, 4, 5, 6. 6 times 50 years, how many years total was that? The answer is 300 years. 14. How are elements created? Where are they created? Well, they're created in the stars. Cooler stars produce small elements. Supernovas create the largest, the heaviest. By what process are they created? They're created by nuclear fusion. That's what's happening in the stars. Write a chemical reaction that will, this should really not be chemical. This should be nuclear. Write a nuclear reaction that will produce sulfur-32 via alpha decay. Okay, so we don't know what we're starting with, but we know that an alpha chunk is falling off of it and we're making sulfur-32. So what must the original nucleus have been? This is thinking backwards. Well, it must have weighed 36. I just added 32 plus 4. And 16 plus 2, it must have been element number 18, which is argon. So just to check yourself, if argon loses this alpha particle, it becomes sulfur-32, which is what this question is asking. Final one, what was the Hanford site? This was a top secret place in eastern Washington, the Tri-Cities area. And at the Hanford site, they made the plutonium for the first atomic bomb and for the atomic bomb that was dropped on Nagasaki. All right. Hopefully your review for the Unit 1.4 quiz goes really